Welcome, welcome to day 200, I think. Um, yeah, day 200. So, nice milestone there. You know, we're slowly getting there. So, I'm gonna hopefully I'm trying to lock in on. These days I've been looking on LeetCode for a bit. I know it's technically not programming, but I count it for myself. I'm doing this for myself, so why I post is kind of more of just an accountability thing. So I've made it really far, so I gotta stick with it, So yeah, let's keep going. I want to do at least like about 30 problems with graph. I think that would be a good number to hone it down, because I don't think I have really good practice with graphs. So regardless, anyways, let's get to it. A DAG, given a DAG with n vertices from 0 to n minus 1 and array edges where edges from... Okay, now this is what I'm familiar with. I'm kind of familiar with this. So edges I from I to I represents a directed edge from I to node I. Find the smallest set of vertices from which all nodes in the graph are reachable. It's guaranteed that a unique solution exists. You can notice you can return it anywhere. Okay. We return 0 and 3. It's not possible to reach all the nodes from a single vertex. From 0 we can reach from... Oh shoot, this is kind of hard. So, find the smallest set of vertices for which all nodes are in the graph are reachable. It is guaranteed that a unique solution exists. Notice that you can reach... Okay. So we need to cover as much ground as possible. So BFS already screams. Let me see, I'm trying to understand. So we have 6 edges, or 6 nodes. 3. Okay. And then, so 0 points to 1, 0 points to 2, 2 points to 5, 3 points to 4, and 4 points to 2. Okay, it's not possible to reach all the nodes from a single vertex. That's true. So really we can reach from here, here, here. Okay. From 3 we can reach 3, 4, 2, 5. Okay, we can go 3, 4, 2, 5. Okay, find the smallest set of vertices from which all nodes in the graph are reachable. It's guaranteed a unique solution exists. It's not possible to reach all the nodes from a single vertex. From 0 we can reach 0, 1, 2, 5. From 3 we can reach 3, 4, 2, 5. I'm still kind of confused. Let me try to understand the second one. 0 goes to 1. Okay, notice that verses 0, 3, 2 are not reachable from any other nodes, so we must include them. Any of those verses can reach from 1 to 4. Oh shoot, that's interesting. Let's really understand. I'm trying to understand how they get to an answer like that, so let's try. Let's write this out, guys, right? So we have nodes. We have this, 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 and then this way, and then up, down, like this. And then we have our values: 1, 0, 1, 2, 0, 1, 2, 4, 5, 6, 3, 4, 5, 3, 4, 5. I actually have no idea how I'm gonna solve this. So I guess we start with 0. Like, I guess the first, or okay, we'll make a little graph here, right? Like we'll pair things up, I guess, right? Like 1, 2, or I guess this node goes to this node. That's what we're saying. The key goes to that other node. 0, 2, 2, 5. 3, 2, 5, 3, 4, 4, 2, 4, 2, 0, 1, 0, 2, 2, 5, 3, 4, 4, 2. Zero, 1, 0, 2, 2, 5, 3, 4, 4, 2. So, I mean, what is the point of doing this? Oh, no. We should do this. Yeah, that's why we do this. Yeah. And I guess we can just go through all the ones. Ooh. We can unpack. Go 2, 5, 3, 4, 4, 2. That is true. Okay. I guess my idea was like we can like pick the largest like pick one of the largest ones, but the problem is I don't know how to get the 3 though, right? So what do we want? Find the smallest set of vertices for which all nodes in the grass are reachable. Okay. Like 0, 3 because uh-oh. This is my issue. I guess we would try doing BFS here. Wait, okay. We go 1, 2. Put 1 and 2 in the thing. Or I guess put 1 in the... Okay, let me see. We'll put 0. Or, okay, 0 is in the queue. Add that to scene. Then go to 1. I add the children, so queue 1, 2, and then repeat. Pop, so 1 is seen. Add all the children of 1. There's none, so that's dead. 2, so that's dead. Pop 2. Add it to scene and add all its children or all its neighbors. That's 5. Pop that. Add 5. Adds all its neighbor. There's nothing, and that's a dead end. Okay. So who are we missing? Okay. We explored as much as we can. From 0, right? Damn, okay, this is hard. Zero, 1, 2, 5. Okay, that's all we've can basically. Maybe a BFS on every single starting point, because we started with adding 0 as our first. Now let's try 2 this time, right? So starting with 0, starting vertice was 0, which equals this set, right? Let's try now 2. Let's see what happens there, right? Let's reset this. So our result, we'll add 2, pop it out, we add 2, add its children, or neighbor, I need to stop saying children. 2, so we add 5. Pop 5, add 5 to the scene, and 5, add 2, we've seen 5, now add all 5, that's it, and that's all we have. So going to 2 and just starting at number 2 will just give us this, which sucks because this set of thing is just a subset of it, so it's just terrible to go through. Let's do another iteration to go through the other one. So let's start with 3. So Q. Okay, let's start with 3. So we add 3, pop it, add 3 to there, add 3 to all its all the things we need. Add 4, pop 4, add 4 to the list. Boom. 3, 4. Boom, I think I found a solution, guys. Basically, and then we know when to stop because we know how big the graph is in 6. And then we'll add these to the set because we've never seen these before, right? Or like superset, I guess. So 0, 1, 2, 2, 5. Okay, now we're almost there. And then 3 and 4, then 5. We're actually, okay, we're almost there now. Right, we're almost, oh wait, we need 3 and 4, right? We're almost there. Now we've hit it. We've hit, okay. We wouldn't add 2 because that's bad thing. And then, okay, we would have added if it added new numbers. So we would have to add that. Okay. I see the solution now. This might be a little bit kind of crappy, but that's all I can think of right now. So we have 2 to 5. We have 3. Okay, we wouldn't add 2 because we already seen these numbers, so 2 wouldn't be in our resulting list. We would add 3 because it gave us new numbers, so we would add that, and then there's gonna be a check if the size of set equals 6. If it is, return immediately. Otherwise, keep going. We're gonna try every single possible vertice. I think this solution will work, guys. All you gotta do is just like think it through. So let's try that. I guess graph very I guess u. What is it? Vertice to edge. What do I call this? Node 1 to node 2. I know this is bad. In edges graph node 1 equals or dot append node 2, and we want a default dictionary, default dict as a list, because we're just goated like that. Okay. Beautiful, right? Let's set up a scene. Let's set up a result, and I guess we can do for every n1. I guess every starting node. I guess for every vertice in graph, print v. Wait, I just need to visualize something real quick. I need to visualize something. Every vertice. So we have 0, 2, 3, 4. 0, 2, 3, 4. Yes, these are all reachable. Like, I can start there. I can't go here because, well, why can't I start at 5? Because 5 doesn't go anywhere. There's just no point. Yeah. Yeah. So these are all the nodes that go somewhere. 5 doesn't go anywhere. This was not in the thing. For every v in graph, that's all we care. We all care about we'll do a b. I guess source equals v, while I guess star q dq I guess we could do a scene here as well. I get now we can add the source here, right? What else do I need to do? Start the algorithm. So dq or q dot pop left right? Oh, no. Okay, and then for every, I guess, see the value, scene dot add value, and for every neighbor in val or graph val, right? For every neighbor in graph val, q dot append neighbor. Okay, but I need to do something special. I shouldn't add should I add it to res instead? Okay, yeah. Right. Okay, scene will be, okay, if length of scene, I guess, we need to compare something. What did we say to, I shouldn't have deleted my pseudo draft, but we needed to see something, like we needed to go and compare this set to something, which was like a super scene, right? All global. Okay, let's call this seen and visited, right? If visited, I guess I want to check is a subset. Oh, I guess do this. If visit or if seen is less than visited, then continue. Or I guess I forget what happens when I do less than greater than on set Python sets. I forgot what that happens. Yes, set 1 is less than equal to set 2 if value is true. If set is a subset of set 2, means that every element in set 1 must be yeah, that's what exactly what I was saying. What if it's opposite? What if it's greater than? Frack. I guess, okay, I don't really I want to skip. Okay, I want to add, basically, that would never be the case. I basically say, I guess, yeah, less than equal to, right, then continue. Otherwise, source, res.append source, right, and return res, right, something like this. If length of res equals n, return res, something like, you know, I think this is a my kind of idea. So we build out our graph, we have a res. Only problem is I'm not adding to see visited. I guess we can do oh, no. Okay. I wanna, okay, I guess, join them together. I guess we can say, otherwise, we do visited equals set, or no, I want to add on union, union two sets Python. What is it? Okay, it's that equals visited visited and seen. Hold on, if that's the case, I don't need to even do this. If length of visited equals n, return res. Let's do this after we add the source and do that. I think this sort of works. Let's break it down. So we build our graph where we add for every starting, where does it go, right, to the list. Creators kind of boilerplate stuff here, res here, visited. We're going to visit every single starting source and start a BFS. So we're going to start with 0. Q is going to go here. We add the source. Create a scene set, right? While Q isn't pop left. So we're going to have 0. Let me actually visualize this because, right, 0, 1. Let me build this out. 1 and 2. We have 2 to 5. We have 3 to 4. And then 4 to 2. Scene equals set while Q pop left. C not add val. So pop left will have obviously the source, which is 0. Check every neighbor. Add that to the queue, right? Oh shoot. Basically try to explore as far, like, how far this source gets us, right? And then we'll be able to see our scene. And basically add everything in visited and seen. Which will be all basically 1 to 5. Res.pend. If our visited equals n, that's a problem. I don't want to add like number 2 because it didn't give us any value. So I need to redo this. I don't want to add 2 because it didn't give us anything new, right? So that's why I need to be more explicit here. So if visited, I need to think, how do I add to the set? Maybe like the union. Like the union here. Okay, I need to think of something. Add this if we contributed to the size of visited. So how do I do that? That's why I have to do if seen is not equal to a subset of visited, right? Then just skip this, right? Otherwise, add that source to our thing. And well, let's, before I even do that, let's, if it's not, then we are a if seen is less than or equal to visited. If seen is less than or equal to visited, then skip this. I don't add the source. And then update or visited. No, update. If it is, if there's new numbers, then we wanna, I guess we still do this, visited, seen. I think we can do that. Right. Right. What do you guys think? I'll run it. What? Dictionary size changed through its iteration. Where am I appending graph? Q to append. What? That should be impossible. Hold on. Where am I messing up? For every v in graph, wait, where am I? Rest of append source, length of it equals random, return that. What? Where am I? Graph should not, I should not be adding to the graph at all. What? I can't loop through the graph? Where am I altering this? Oh. Huh? I can't do this? Hold on, let me see something. Wait, I thought... Yeah, this is key. If I just iterate, maybe... What? What am I missing, guys? Come on, who do I mess with? I don't mess with anybody. Does this like mess with the thing or something? No way. I've never seen this before. Dictionary change size during its for every v in graph. I've never seen this error before. Why would, who is, there's nothing that's altering, does like accessing of, oh wait, val q dot pop left, scene dot add val, for every neighbor in graph v. Okay, hold on. Can I just call it source then? I don't know what makes a difference. Runtime, why? Who is messing with this? Does this cause that? What? I gotta be iterating through a dictionary wrong. Iterate through. Oh my god, hold on, I know why it's this. Because if like 5, right, does not exist and it's gonna automatically add it. And that's actually altering the glad. Oh my god, default dictionary actually screwed me over. Like, wait, what? Yeah. Like, I added 5, right, to my thing, and then it tried to access 5, and accessing 5 changed the list. So, no. Oh, wait. I guess if val not in graph, continue. Yeah, and then just go here. Well, we can add him. We definitely want to see him, right? Okay. I see the vision, guys. Come on, please. That was a really bad bug. That was such a crappy bug. Just give it to me, please. Just give it to me. I'd spent a little too long on this, but I'm kind of rusty, so. Oh my god, tell me this TLEs. Oh wow, of course. Oh, it's got a wrong answer, never mind. Okay. Output is 124 and I got 24. Okay. Maybe my subset kind of messed it up. I guess, hold on, n minus 1? Does that mess things up? I think that messes things up, yeah. No, we're missing a value. Why would we want to? Yeah. Okay, so wait, why is this wrong again? We missed a 1. Oh, we added an extra. Oh crap. Okay. Okay, that is a lot more complicated than that. So that means we shouldn't add 1, but why? Because we want to be greedy, I guess. Yeah, I can't. This is too hard. Man, I'm freaking so bad with this, bro. Topological sort is crazy. Something with Indegree. Give me the Python solution. I'm actually stupid, bro. What is an Indegree, bro? I forgot Indegrees. I'm gonna crash out. The number of edges pointing towards a particular, counting the number of incoming edges to that. Oh yeah, we just basically count that and add it to the list. Basically, the highest amount of Indegrees. Oh my god, hold on. That theory pissed me off, bro. So, Indegrees. Create an Indegree of list size n for every edge in that, right? Plus 1. Answer for every range. If Indegree is equal to 1, answer dot append. Iterate through all the vertices and add the ones with an Indegree of 0 to answer the list. Wait, what is an Indegree again? I'm still kind of not trying to understand. Okay, basically Indegrees are iterate through all the edges and update through Indegree. Oh my god, bro, that's so stupid, bro. I didn't know the theory. Find verse that we cannot reach from another index. Now let's solve the reverse problem. Find the vertices that we can reach and subtract the number of total. All nodes minus reachable. That's nice. That's a nice clean solution. Count nodes with 0 indegrees. Okay, I don't. That's what I don't understand. Is that like nodes, vertices that have no? I don't get it. That's a disgusting solution. Don't ever post that again. Bro. Indegree, a number of edges going into a node. Why do we... Oh, I see. Okay. So that, well, let's see. The number of nodes so that have 0. So 5. Why don't we add... Oh, no, that's not true. So 0 is 1 because there's nobody going to 0. That is so facts, bro. Oh my god. 3 is also 1 because there's nobody. Like, I think the literal hint was right here. Notice that 0, 3 are not reachable. Oh my god, I'm such an idiot. Now I know that technique, so I can definitely code it up. Alright, this is... How long did I take on this? 42 minutes. I'm fucking cooked, whatever. Okay, so basically, I guess Indegree. What size of this times... And for every edge, or v in edges, I guess we can do right Indegree of, I guess, v increment 1. Res this, turn res very I in range of length of n if Indegree of I equals 0, res dot append I. Oh my god, that's such a simple answer. If I just knew the theory, man. Anyways, thanks for watching, guys. I'll see you guys tomorrow. Peace.